Today we're presenting you with our final project, stray light mitigation using Vane structures.
Hi, my name's Avi.
And my name's Sutton.
And just how we were hiding, stray light might be hiding in your optical system.
In this project, we will be evaluating the effectiveness of Vane structures in reducing stray light in an astronomical telescope. Before we get into the procedures, can you tell us a little about stray light, Avi?
Sure. In simplest terms, stray light is unwanted, unintended light that enters an optical system and interferes with the intended image or signal. It is commonly caused by light scattering off surfaces, dust, or any imperfections in the optical components. Stray light even affects your iPhone, as you can see by this green halo and streaks across my face from the sun.
The funny thing about stray light is that it doesn't have to be a huge issue. There are many different ways to mitigate stray light in an optical system, but the issue is often neglected until the experimental phase of development, and by then, designers realize they have to undo countless hours of work to fix it.
That's right. Now, one of the most common ways of eliminating stray light in a telescope is by adding vanes. What's a vane? A vane is a structure used to block stray light paths without reducing the field of view of the telescope. But where do we put them? Luckily for us, the book Stray Light Analysis and Control by Eric Fest tells us exactly what to do using a simple formula. Using this formula, we designed and 3D printed 6 vanes to add into our telescope.
Now that we've gotten an overview of stray light and Vane structures, let's get into our actual experiment. So this is our experimental setup here. We have our telescope on a 360-degree rotation stage. Here is a standard astrophotography camera that feeds right into my computer over here and gives us a live output. Across the room, you will see a source with a 1mm aperture and a collimating lens. Now, for our experimental procedure, our data collection, what we would do is we start at 0 degrees on the rotation stage, and then we rotate it 0.25 degrees, or a quarter of a degree, starting from 0 and ending at 2.5 for a total of 11 measurements. So this is our data collection process. Basically, we have the app here that is connected to our astrophotography camera. Now, once we are in the angled position that we'd like, we snap a picture using this button. We put that file into MATLAB, and once we have all of them from 0 to 2.5, we get a nice pixel count.
We repeated this whole procedure twice, once without any vanes in the telescope, and once with these 7 vanes. To take the vanes in and out of the telescope, we would take off the top of the telescope and slide them in or out one by one. Here are our results. The red data points represent the normalized pixel count per degree for the telescope without vanes, while the blue represents data with vanes. We see about a 50% decrease in stray light with the vanes, though our data is likely exaggerated by some slight misalignments.
In the College of Optical Sciences at the University of Arizona, many research groups do stray light analysis on different types of optical systems.
The Large Optics Fabrication and Testing Group, led by Professor Daewook Kim, focuses a lot on stray light analysis, otherwise known as non-sequential ray tracing.
And whenever you build actual system like a mobile phone camera or space telescope detecting exoplanet, you must analyze your system non-sequentially.
One such project that is currently being worked on in the group is Luke Mayer's Scattering Properties of Black Pigments project. In this project, he uses computerized models along with experimental data from a real telescope to study the effectiveness of different black paints on the mitigation of stray light.
It is absolutely the most important skill set, one of them. Thank you.
Thanks for watching. We hope you learned something about stray light and one way to mitigate it.